Assalamualaikum warahmatullahi wabarakatuh. My name is Anessa Nurazmi. I'm from Magister of Chemistry, Gadjah Mada University. Today, I will present a paper entitled Electrochemical Paper-Based Analytical Device EPID Using Immobilized Prussian Glue and Antibodies for the Diagnosis of Leishmania by Papi et al. 2025. This presentation is part of the clinical forensic analysis course under the supervision of Prof. Dwi Siswanta. And then the study introduced a new low-cost electrochemical diagnostic method that aims to make disease detection simpler and more accessible. Leishmaniasis is disease caused by Leishmania parasite, which are spread by the bites of sandflies. It affects people mostly in poor and tropical areas with up to 1 million new cases each year. These diseases can appear in the three forms: cutaneous, mucocutaneous, and visceral leishmaniasis. Common diagnostic methods such as parasitological and serological tests like ELISA or Western blot can give accurate results. However, they are expensive, take a long time, and require special laboratory equipment. Because of this, there is a strong need for diagnostic tools that are simple, fast, and low cost, especially for use in remote or low resource areas. Electrochemical biosensor, especially immunosensor, are a good alternative for detecting infectious diseases. This device change the reaction between antigens and antibodies into electrical signal that can be measured. They have several benefits such as being portable, cheap, small, sensitive, and selective. Still, traditional electrochemical systems have some problems, including unwanted molecule absorption, unstable biological layers, and difficulty in reuse. To solve this problem, paper-based analytical device or PADS have become popular. Paper is cheap, disposable, and good for detection biomolecule. And then when electrochemical detection is added, the system called an electrochemical paper-based analytical device or EPAD offer both good, sensitive, and easy to use. In this study, a qualitative EPAD was developed to detect Leishmaniasis amazonensis antigens. The device used antibodies and Prussian glue as the redox mediator on the paper base. Built as a sandwich type immunoassay, the EPAD provides a sample, fast and affordable, while to diagnose leishmaniasis, making it useful for area with limited medical research. Circular paper discs, 1 centimeter in diameter, were punched from filter paper and serve the main platform for the EPAD. The discs were immersed in precious glue solution and placed in ultrasonic bath for 2 hours to promote uniform coating of the paper fibers. After coating, the paper was cleaned using sodium chloride and 20 solution to remove unbound materials. The coated paper were dried at 16 Celsius for 12 hours to stabilize the precious glue layer. The precious glue acts as electrocatalyst and enhance the detection signal during electrochemical measurement. Next, horseradius peroxide or HRP was immobilized on the paper to evaluate the detection mechanism using hydrogen peroxide. The activation step was done by adding ADC or NHS to create a reactive site for antibody attachment. After activation, antibodies against Leishmania amazonensis were attached to the paper through covalent bonding, forming the recognition layer. The immunoassay was designed using a sandwich type configuration similar to an ELISA test. It is used two types of biological elements: capture antibody immobilized on the paper surface, and then the detection antibody HRP label and added later. This type include capture antibody specific to Leishmania amazonensis are then immobilized on the paper. And the free sites on the paper are blocked with BSA, or bovine serum albumin. And then the negative sample, no Leishmania antigen, is applied to the device, and then no enzyme or HRP remains on the paper to produce an electrochemical signal. A positive sample containing the Leishmania amazinensis antigen is added. When hydrogen peroxide is added, the HRP catalyst its reduction reaction, and then electrons are transferred via Prussian's glue, creating a strong measurement current. In this curve, blue curve for negative sample, low current because no HRP is present. And then red curve for the positive sample, higher current due to the HRP catalytic activity. HRP enzyme reduce hydrogen peroxide to water, producing electron flow through precision glue. And precision glue acts as a redox mediator, switching between oxidized or PV and redox PB forms. Electrochemical measurement. Experimental setupnya measurement were performed using screen printed carbon electrodes or SPCA connected to palm sense portable potentiometer. The experiment were managed through PST race software. Cyclic photometry or CP to characterize the redox behavior of Prussian's glue and confirm stable coating. Multiple pulse amperometer or MPA to record detecting signal during the immunoassay. And optimized condition, the method way was tested with human serum sample from two groups. Positive sample from patient infection with Leishmania amazonensis confirmed by PCR test, and negative sample from healthy volunteers. Blood was collected by trained personnel, and then the centrifuge and the serum storage at -20 Celsius until analysis. Each sample was tested with both the new EPAD method and PCR to compare results. Selectivity tests were also performed using sample containing the yellow fever virus, confirmed that the EPAD didn't react with other infection. All experiments were conducted according to ethical standard approved by the Research Ethics Committee of the Federal University of Paraná, Brazil. In the panel A, the paper electrode surface is first modified with Prussian's glue, which acts as a redox mediator that facilitates electron transfer. Specific anti-Leishmania antibodies are then immobilized on this surface using ADC or NHS chemistry, forming covalent bonds between the antibody and the carboxylic group on the electrode. This layer of antibodies function as the capture element, ready to recognize and bind the target antigen from the sample. In the panel B, the functionalized electrode is now ready for the detection step. When a biological sample, such as human serum, is added to device, it's come into contact with the antibody-coated surface. If the sample contains Leishmania antigens, they will specifically bind to the immobilized antibodies, forming the first layer of the immunocomplex. If the antigen is absent, the surface remains unreacted. Panel C illustrated what happened when a negative sample, a sample with no antigen, is applied. Even though the serum interacts with the antibody surface, there is no antigen available to bind. This means the antibodies remain free and the surface structure doesn't change significantly, and as a result, no antigen-antibody complex is formed at this stage. In the panel D, after the incubation step, the HRP label secondary antibody is introduced. However, since no antigen is present, this enzyme-labeled antibody has nothing to attach to and is removed during the washing step. Because HRP is absent on the surface, the enzymatic reaction with hydrogen peroxide doesn't occur. Consequently, the electrochemical current remains unchanged and high, representing negative result. In the panel E, show the opposite condition when the positive sample contains Leishmania amazonensis antigens. These antigens molecule specifically bind to the immobilized capture antibodies, creating the first half of the sandwich or antibody antigen. This binding event is highly specific and ensure that only Leishmania target trigger the next step. These antigen attachments slightly reduce the available surface area, which will later affect the electron transfer efficiency. In the panel F, the HRP in the panel F, the HRP label secondary antibody is added to the electrode. It recognizes and binds to another site on the antigens, completing the sandwich structure, capture antibody, antigen, and HRP conjuncted antibody. After this, hydrogen peroxide is introduced as the enzyme substrate. The horse peroxide or HRP catalyze the reduction of hydrogen peroxide to water, and in this redox reaction, electrons are transferred through the presence blue or PB layer on the electrode. This process generates an electrochemical current. However, because the enzymatic reduction consumes part of the electroactive species, the measure current decreases compared to the blank. This drop in current represents the detection signal confirming that Leishmania antigens are present in the sample. Panel G summarizes the detection and signal mechanism. On the left, the graph yellow circle highlights the area containing PB nanostructure, while the yellow around point to antibody particle distributed across the paper surface. And then photometric behavior of the system. In the figure, cyclic photograms display the characteristic redox behavior of the presence blue modified electrode under the three different conditions: blank, control, and detection. The gray curve for the blank correspond to the electrode before any biological modify or antigen addition. It shows two clear redox peaks associated with the reversible transformation between Prussian blue and Prussian white. This confirmed that Prussian blue was successful disposite and is electrochemical active. The blue curve for control represent the signal obtained after antibody immobilized and blocking, but without the presence of the Leishmania antigen. Here, the redox peak slightly decrease in current compared to the blank and indicating that the antibody layer partial blocks electron transfer at the surface. And then last, the red curve for detection show the photometric response after the introduction of the antigen and HRP label antibody, forming the complete sandwich immunocomplex. A more pronounced decrease in current is observed as indicating by the bracelet in the figure. This reduction is peak current occurs because the antigen-antibody complex acts an insulin layer that further limit electron transfer between Prussian's blue and the electrode. Overall, the progressive decreasing in current intensity from the blank to the detection condition confirm that each modification step was successfully achieved. The biosensor actively responds to the presence of the target antigen. Figure B present a bar comparing the relative current intensity for different EPAD configuration. One control, the electrode coded only Y presents blue and antibody showing the high current 100%, representing the reference condition. And then this LAP-AB start the electrode after exposure of the Leishmania peptide or LAP and label antibody a moderate current drop 75 until 18% of course, indicating partial surface coverage by antigen. And then AB and AB start the configuration using both primary and label antibodies, but without antigen, showing a similar decrease due to steric hindrance from protein absorption. AB, BSA, LEP, AB start the complete sandwich type immunoassay, including blocking with BSA, antigen, and HRP label antibody. And then this stop showing the lowest current 30% confirmed successful antigen detection and formation of the immunocomplex layer that hinders electron flow. The error bars represent standard deviation, demonstrating the method reproducibility and stability. The clear difference between the control and detection configured indicating that the electrochemical signal is specific to antigen-antibody binding rather than non-specific interaction. And then photometric behavior of the system for a selective and control test. Selectively blank versus YFP, the sensor was tested with yellow fever virus, which acts as concomitant and interfering substance. The control is a gray bar. For YFP, show signal not significantly different from the blank. Negative sample. The negative sample initially gray control bar show a high response similar to the blank. However, after the addition of lab or LAP cyan bar, the text that is yield a positive result, which is visual a signal drop. Positive sample, the positive sample gray control bar already show a strong response, a low signal around 40% after the addition of LEP cyan L bar. Its response future intensive indicated by an even more drastic signal drop to around 25%. And then B, application on human serum sample. Patient sample P1, P2, P3. The sensor was tested using blood serum from 3 volunteers diagnosed with Leishmania. All the 3 sample, P1, P2, P3, showed a marked response compared to the blank. This is seen in the significant signal drop. P1 and P2 drop to 16% and the P3 drop to 13%. Control sample N1, N2, and 3, the sensor was also tested on 3 controls, non-infected individuals. The result show no significant variance when compared to the blank. The signal remained high around 92 until 98%, similar to the blank. Statistical validation, the text confirmed that the result for P1, P2, P3 are statistically significant. The calculated t-student value exceeded the critical t-value at the significance level of alpha, which prove a real difference from the control. In the contrast, N1, N2, N3, and result were not statistically different from the blank. Thus, as observed in Table 1, electrochemical based bioassay are successfully applied to the detection of different Leishmania target, showing remarkable distinguishability and sensitivity between positive and negative sample order diseases. Advantage of the EPID method. This is achieved through cloud production caused by using paper substrate and unmodified screen-printed electrode. And then two, the device offers simplicity and easy of use. Its straightforward operation typically require minimal training. And the third, it is designed to be a valuable tool for the rapid and reliable diagnosis, providing and rapid qualitative diagnosis and rapid result. This is a key advance over time consuming conventional tests. The EPID is portable and can be miniatures, making it ideal for on-site monitoring and field application. By being low cost and easy to use, the EPID enhances its accessibility, making it practical solution in public health, particularly in underserved region. And then this contrasts with conventional methods that require centralization in special laboratories. The immunoassay demonstrated good reproducibility and selectivity as well as good sensitivity. And then as a paper-based device, it has the ability to operate with minimal sample quantities. And then the last, the paper platform is disposable, which avoid challenge related to regeneration the sensor for repeat use. Limitation of the EPID method, it is explicitly described as qualitative electrochemical paper-based analytical device. This means it's over a simple binary or a categorical output, indicating the presence of absence of a specific target analyte rather than its precise concentration. The paper notes that while quantitative response is often highly desirable, this sensor is intended for situations where rapid and straightforward detection is prioritized over detailed quantitative analysis. Potential future application for clinical analysis. And the method is described as highly suitable for point-of-care diagnostic and particularly suitable for field application. Its portability, rapid result, and easy of use are key. And the second, the platform is a valuable tool for the rapid and reliable diagnosis of neglected diseases, with Leishmaniasis serving as the primary example. And the third, the sensor is presented is a practical solution in public health for addressing critical healthcare needs in the underserved population. It can be used as an accessibility diagnostics tool in remote and economical disadvantaged regions. And the last, the EPAD holds significant value in the clinical diagnosis, where rapid and straightforward detection is priorities over waiting for complex and quantitative lab results. That's all my presentation, more or less, and apologies. Thank you for the attention. Wassalamualaikum warahmatullahi wabarakatuh.